Cyclops. We listen to plants. Now, to start today, I wanted to finally talk about how to actually understand plant voltage signals. Let's put that in writing. Plant voltages and our understanding of them. You remember that in past recordings we've talked about the general setup of the plant voltage recorder on a tree, as one example that you can see in the field recordings on the conifer tree. Right? So our basic setup is our tree, soil level, and you'll forgive me that what I'm going to draw right now is not the conifer tree because I can't draw them. So I draw this instead. And our voltage recorder, as you also remember, has 3 electrodes. Ground, this one we call E1, located at the base of the stem. And then this one, called E2, approximately, in our case, the space between here is 2 meters. Right? So all of these have a connection with our recording box through normal electrical wires. 3 wires. This is our recorder. I've explained in the previous video how this one works, how it measures the voltages produced by these 2 electrodes, E2 and E1, and how it writes them out to SD card, to a micro SD card. So far so good. Now, the setup that I've done in the field has been running now, what is today? Today is 7th of April, and it has been running since at least a month, over a month. It has been running over a month now. So we have at least 30 full days of recording. What I'm going to show you now is the recording I made over the duration of one single day. And this recording looks like this. What do we see here? Don't mind these scales at the side, they are not something, they're percentages, and they're not really that important at the moment. So we have two different streams of recording. As I said, this is one full day, and it goes, as you can see here, from midnight to midnight. Midnight, the 2nd of April, to almost midnight, the 3rd of April. This is E2, so the voltage is recorded from this electrode. This is E1, the voltage recorded from here, both reference to graph. Now you see this and you think, well, what can I do with this? This is pretty much random, right? This is not really something I can use to say, well, at this point in time, let's say 6 a.m. April 2nd, my tree is doing this and that. Well, it might look at that at the first impression, but what I'll tell you is look at this as if it was an X-ray picture. For those of you that have ever seen X-ray pictures, either of broken bones, of skulls, of chests, you look at these X-rays and you see just clouds of white over a black background, and they don't make any sense to you. And then the doctor or the specialist comes in, looks at them for 15 seconds and says, oh yeah, besides the broken bone here, you have this, that, and that. And to you it looks all the same. And why can they do this? They can do this because they have seen so many X-ray pictures that the smallest details in them are evident to them, and they know exactly what they mean. And because they've seen so many of them, even very small changes have a distinct meaning. And I'm telling you this because it is exactly the same way with these voltage recordings. The small details in this picture, the small details in the sequence of voltages, can be interpreted in exactly the same way, and they all have meaning. So, to make an example, what would you think that a plant is most likely to respond to? Well, plants obviously need light, water, and nutrients. So whenever these things change, when light changes, when water availability changes at the root level, then the plant has to respond in some way. These responses we see in the voltages. So the most obvious response we would expect from the plant is a response to light. Sunrise and sunset. And how do we see this here? I've already given you a spoiler basically by saying that this started at midnight and ended at midnight. So it's not difficult. It's not difficult to guess that this graph in about this area here, from here to there, is daylight and the rest is night, right? No, I'm more or less correct. This is about 7 a.m. in the morning, and this is 7 at night. It's a bit late. So daylight is more or less this. That's correct. Now when we look at this, when we look at E1 for example, you don't see, well, apart from maybe this little drop here after sunrise, we really don't see many distinct features in there that would tell us, oh yes, that coincides exactly with the daylight period. But now let's have a look at E2. What do we see that might be happening between these 2 points, sunrise and sunset? Or what do we see that happens only outside these 2 points, before sunrise and after sunset? What could that be? So our attention falls immediately on these areas here. Where things get noisier. You see that, well, let me call them, these up and down wiggles that you see. They have a larger intensity here and there when we compare them to the daylight period. Let's ignore these 2 spikes for a moment. So that would be our first obvious guess about daylight or not daylight. The amount of wiggles, or in technical terms this is called the amplitude of the voltage fluctuations, would be an indicator for night in this case. Because the higher the amplitude of the fluctuations, or phrased differently, if the amplitude of the fluctuations is high, like here or like there, we are at night. While if the amplitude is low, we are in the daylight period. This would be a first guess, or a first hypothesis, if you want, that we could make after seeing this, just this single 1-day recording. So far so good. So what we have to do now is look at other recordings of other days and see if this hypothesis holds for them as well. And if it does, then we have ourselves a nice little, a nice little first step in understanding plant voltages. So let's do that. Let's look at another day, a different recording, and see if in E2 we can see the same dynamics.